Hi there. So today I'd like to talk to you about atomic force microscopy. We're going to go over some of the basics here. So AFM, or atomic force microscopy, provides a 3D profile of the surface on a nanoscale by measuring forces between a sharp probe, which usually has a radius of curvature of, say, 10 nanometers or less, and a surface at a really short distance from each other. So you can bring it down to within less than a nanometer to 10 nanometers or so for probe sample separation. And the probe is supported on a flexible cantilever. And then the AFM kind of gently touches the surface and then records the small force between the probe and the surface. And then by maintaining a signal in a feedback loop, then you can generate a three-dimensional topo map like some of the ones that you show here. So this was taken by me for a project that we did on measuring the topography of wear surfaces on Neanderthal stone tools, for example. So how does it measure the forces? Well, the probe is placed on the end of a cantilever, which you can think of as a spring, and the amount of force between the probe and the sample is dependent upon the spring constant or stiffness of the cantilever, and typical spring constants could range from, say, 1/10 of a Newton per meter all the way up to on the order of, say, 10 or 20 newtons per meter, but 1 Newton per meter is pretty typical. And then the distance between the probe and the sample surface is also going to determine the force, because the force is described by a Hooke's law, where F is equal to minus kx, or F is equal to kx as you push into the surface. So you have your spring constant k, and then the tip surface distance, which is your x, and so you've got a dependence there on those two things. So typical forces can go down to, say, nanonewtons or a fraction of a nanonewton, and high forces might be a millinewton, but a typical would be, say, somewhere in the micronewton range. So the probes and the cantilevers are typically made from silicon nitride or silicon, and they follow some of the same techniques that are used in lithography for making chips and integrated circuits. So different cantilever lengths, materials, and shapes allow for varied spring constants and resonant frequencies. And a description of the variety of different probes can be found on various vendor sites. So here I show some images from Bruker AFMprobes.com, for example, and Bruker is a dealer of both AFMs and AFM probes. And then here's another one made by a different company, NanoAnalytic. So the probes can be coated with other materials for other kinds of modes, for example, chemical force microscopy, magnetic force microscopy, scanning capacitance microscopy. You might want to coat your probe with something that is magnetic or conductive, depending upon your technique. You might also want to functionalize the probe and coat it with other types of chemicals or thin films, depending on the application or what you might want to do. So how do you make a contact mode image? Well, the motion of the probe across the surface is controlled using a feedback loop and a piezoelectric scanner. So piezoelectric material is a material that if you apply a voltage, it will deform the crystal, and you can apply a known voltage, getting the crystal to expand or contract by some known amount, and that's how the motion of the cantilever is controlled. And then the deflection of the probe is measured by a beam bounce method. So you have a laser that's bounced off the back of the cantilever onto a position-sensitive photodiode detector that usually has 4 quadrants. The detector measures the bending of the cantilever as the tip is scanned over the sample, and then you have a feedback loop which maintains a certain position of the laser on the photodiode as the tip is scanned over the sample by adjusting the cantilever position by applying a voltage, a known voltage, to the piezo. And then the necessary movement of the piezo is monitored for each pixel in the image, and then that's used to create a topography map. And so that's how contact mode images are created and generated. Now, the feedback loop can monitor other types of signals. For example, if you're doing tapping mode or non-contact mode, the feedback loop, you still have the laser bouncing off the back of the cantilever, but instead that laser beam is allowed to move or oscillate, and then a certain amplitude of oscillation, for example, is maintained. So the same type of concept for different modes, but slightly different signals monitored. So the types of forces that are measured, if you look here, as you approach or vary your tip sample distance, then you're getting into different regimes of forces between the tip and the sample. And so those are marked here on this figure. The dominant interactions at short probe sample distances in the AFM are these van der Waals interactions. Long-range interactions like capillary, electrostatic, and magnetic are significant further away from the surface, and these are important in other SPM methods of analysis. We'll talk about other modes at the end of the talk. But during contact with the surface, the probe predominantly experiences a repulsive van der Waals force, and this is contact mode, and that leads to the tip deflection described in a previous slide. And then as the tip moves further away, then you have your attractive van der Waals forces, and those are dominant in non-contact modes that we'll talk about here in a second. Okay? So there's three primary imaging modes in the AFM. These are the typical ones that you'll find on other AFM. Like I said, we'll discuss other modes of operation later in the talk. But the three primary ones are contact AFM, and that has a tip sample separation of less than half a nanometer, say. And then you have intermittent contact, or more commonly known as tapping mode AFM, where the tip and cantilever are oscillated over the surface, and then the tip gently taps the surface at the bottom of that oscillation. And in those, the distance between the tip and the sample ranges between half a nanometer to about 2 nanometers. And then you have non-contact AFM, where your tip of your surface never actually touches, the tip never actually touches the surface, but it's wiggled over the surface. And that can get further away, up to 10 nanometers away, for example. So let's first talk about contact mode AFM when you're in that repulsive van der Waals regime. So first of all, you only want to do this with samples that have relatively hard surfaces because your tip is constantly touching that sample. And so that leads to one of the main disadvantages of contact mode AFM, which is that the tip can actually damage the sample or deform it if the sample is too soft. But when you're in this repulsive van der Waals regime, your spring constant of the cantilever is less than the stiffness of the surface, and so the cantilever bends, and the force on the tip is repulsive, and then you maintain a constant cantilever deflection using that feedback loop I described earlier, and the force between the probe and the sample remains constant, and then you use that to generate an image of the surface. So the advantages are that this is fast scanning, and it's good for rough samples, and it's used in friction analysis, which I'll talk about in just a second. But the disadvantages, of course, are that it can scratch the surface, as we talked about earlier. Now, if you don't want to deform or scratch your surface, then you can stay in contact mode and switch to a lower spring constant cantilever because, of course, at a base Hooke's law, F is equal to kz. So if you switch to a lower spring constant, you're not pushing as hard. Or you can switch to one of the tapping or non-contact modes, and then that is less likely to deform your sample. However, sometimes, and this is worth mentioning, researchers want to scratch the surface for whatever reason. Maybe they want to write a pattern on the surface or deform the surface on purpose. Like, for example, this research group here, whose image I stole and credited, they introduced defects like scratches with the AFM, and then they submerge the surface in a liquid and do an electrodeposition, electroplating basically, onto that surface. And then the metal preferentially deposits on the scratch sites, because the way that they deposit it is they apply a voltage to that surface, and of course when you apply a voltage, your electric field is going to be higher at areas that have smaller radius of curvature, and if your electric field is higher, then you get more electrodeposition of the metals at that point. And so they're using it to nano pattern their surface by scratching it. Another benefit of contact mode that you might want to exploit is that it can measure friction on the nanoscale. So you can see what typically happens in an AFM image is that you scan a line and then you scan back over that same line. So it scans each line 2 times, the back and the forth. The lateral forces, though, that are on the cantilever can cause it to bend sideways, as you can see in this little cartoon over here. And that can cause the deflection of the laser spot on the photodiode from left to right. Well, you can monitor the deflection of the laser spot on the photodiode voltage as it deflects from left to right, and then that can be used to generate a signal, as is shown here. And then that signal, the voltage of the signal, can be related to the force, the lateral force or friction of the tip on the surface. So higher friction surfaces deflect the cantilever more laterally, which means that you can measure a higher friction force. So you can actually measure friction on the nanoscale, and that's been done a lot. I've done it myself, for example, during my PhD thesis. Okay, moving on to another really common mode in AFM, we can also talk about tapping mode, also called intermittent contact mode. So in this, the imaging is similar to contact. However, in that mode, the cantilever is oscillated at a resonant frequency. Resonant frequencies typical can be in the tens to hundreds of kilohertz range. They have oscillation amplitudes of 20 to 100 nanometers or so typical oscillation amplitudes. So during this mode, the probe lightly taps on the surface sample during the scanning, and it contacts the surface at the bottom of the swing. And by maintaining a constant oscillation amplitude, that means that you're maintaining a constant tip sample interaction, and that allows you to generate a map of the surface. So the advantages of this, it allows high resolution of samples that are easily damaged or loosely held to a surface, and so it can be good for soft samples like plastics, polymers, or biological samples. However, it's more challenging to do this in liquids. Typically, if you want to do imaging in liquids, you do it in contact mode. It's not impossible, but it is more challenging, and sometimes slower scan speeds are needed. However, I'd like to say that these days, tapping mode is one of the most common modes that people try when they just stick their sample in the microscope. They just kind of default to tapping and then go from there, depending on what they want to figure out. There's another mode called non-contact mode. This is a lot less common because it's more difficult to do, but this images in the attractive van der Waals regime. And in this mode, the probe doesn't actually contact the sample surface at all, but it oscillates above the surface, kind of in this adsorbed fluid layer on the surface during scanning. It's important to realize or note that all samples that you image in air and ambient conditions have some liquid absorbed on the surface, and this is just due to the humidity in the air. It doesn't have to be you spilled water or put water on the surface. So that's important to remember whenever you're doing AFM. So using a feedback loop, you can monitor changes in the amplitude of oscillation due to those attractive van der Waals forces, and then you can measure your surface topography. Now, of course, the advantages here are that there's very low forces exerted on that sample, and that means that your probes last a really super long time, and you practically never damage your surface. However, this mode often has lower resolution, and contaminant layers on your surface can interfere with the oscillation. So oftentimes people don't do this mode unless their AFM is in an ultra-high vacuum chamber, and that allows you to do the best job of imaging. Another thing people typically like to do with atomic force microscopy is to take force curves. Okay, so what you do in a force curve is you measure the amount of force felt by the cantilever as you bring your probe tip into the surface and then push into the surface to some specified force, and then you begin to pull out of the surface and release. So you're going in and out. So this isn't raster scanning where you're scanning in sort of an array over the surface. In a force curve, you're staying at the same point laterally on the surface, and you're moving the tip in and out like that. Okay, so there's a little cartoon here. First, the tip starts and it's not in contact with the surface at 1. That's in the red part of the curve here. And then eventually, it gets close enough to the surface where those attractive van der Waals forces take over, and it'll kind of snap down into contact with the surface, and that's shown here in the cartoon at 2. And then you begin to push into the surface, and eventually the cantilever deflects and bends upward until you reach whatever specified force or deflection that you set for your force curve. And then it starts to reverse direction and pull back out. Now generally what happens is your tip wants to stick to the sample due to adhesive forces between the tip and the sample. So generally when you pull back out, you go to a larger distance away from the surface before that tip snaps loose. And that's indicated here at position 4, where the cantilever is actually bending downward now due to the adhesive forces in between the tip and the sample until it gets far enough away, and then it kind of snaps loose and back to its free position. So that's what you see in a force curve. Force curve analyses can be used to determine chemical and mechanical properties like adhesion, elasticity, hardness of a surface, and rupture bond lengths. Now the slope of the deflection, which is shown here in the cartoon at C, actually provides information on the hardness or stiffness of the sample from that F is equal to KZ equation. And the adhesion provides information on the interaction between the probe and the sample surface as the probe is trying to break free. So to measure the adhesive force, you just measure how far down the deflection is here at point D when it snaps away from contact. And then, of course, lots of times people will functionalize their probe. They'll coat it with a thin film of some chemical of interest. And then that can be used to measure the interaction of whatever you've got on your sample with whatever your thin film coating is, and that might be of interest for particular studies. Now moving on, sometimes topography really doesn't tell the whole story. So sometimes you might want to use one of the many other modes that are available in AFM. So for example, lately I've been kind of interested in doing quantitative nanomechanical mapping, or QNM mode. And in that one, what it basically does is you're doing sort of a tapping mode, but at each tap, it's measuring the stiffness from that force curve regime. It can measure the stiffness or modulus of the surface, and it can also measure an adhesive force. And so you're getting that kind of information that you might get out of a force curve at every single data point on the surface. That's QNM mode. Okay, so that's really useful. You can also do tunneling AFM, TUNA, or conductive AFM, often abbreviated with CAFM. And both of those modes, you can measure the conductivity of your sample, which might be of interest. You can also do MFM or EFM modes. MFM means magnetic force microscopy, and EFM means electric force microscopy. And in those, you're kind of doing a lift. So you'll scan over a line, and you'll use that to figure out what the topography of the surface is. And then you kind of lift up and move the AFM tip back over that same region of the surface, except this time it's not touching. Say it's maybe 10 nanometers away from the surface. And then you measure the deflection of the cantilever due to the electric or magnetic fields that cantilever might experience. Now, lots of times when you're doing MFM or EFM, you need special probes that have either conductive coatings or coatings that are magnetic. Okay, so these are specialized tips that you want to use. You can also do electrochemical AFM mode, and that you generally have your sample and tip submerged in some sort of liquid solution of interest, and you're applying a bias voltage to your tip as you scan it across the surface. And then you measure changes in the current between the tip and the sample when you're doing that. And you also measure changes in topography, because you can get deposition or changes in the surface when you're scanning your tip with that electric field there in the presence of some of these liquids that you're interested in doing. A lot of chemists use this mode. You can also do scanning capacitance microscopy, and this is sometimes similar to the MFM or EFM modes that I discussed earlier, except when you're in your lift mode, you're measuring the capacitance of the surface. There's a little image here that I've taken from Bruker of a scanning capacitance mode image. So the one on the left is just the topography, and so you can see that there's a patterned surface here, maybe in an integrated circuit or something. And then if you look at this SCM image of that same region, then you can see that there's features present in that image that aren't present in the topographical image here on the left. Specifically, you can see these little dots, and within these dots, if you know what you're looking at, then this represents areas that have been heavily doped by arsenic ions for that particular sample. And so you can see that the capacitance is different because the composition, the chemical composition of the surface is different. So that could be really useful for a lot of different applications. And you know, there's a lot more modes out here than I really have time to discuss. They're coming out with new modes all the time. Even in the 20 or so years that I've been doing this, they've come out with a ton. And it seems that AFM is more versatile and can do even more things pretty much much every day. For example, just the other day, I saw that they had paired up an infrared spectrometer with AFM so that you could really take an infrared spectrum, or at least look at peaks of interest from the infrared spectrum and scan over the surface and get chemical identification while you get a topography map. So, I mean, really just, stay tuned because they're coming up with these new modes all the time, and it's really fascinating. Some of the limitations that you might experience with AFM are that you can use it to image all kinds of samples. It doesn't matter if it's a semiconductor or conductor or an insulator, so that's actually an advantage. However, there are issues in achieving the resolution that you might want on each one of these samples. So for example, if you have a very rough sample or a sample where the slope is really steep as the topography varies, like so for example here you've got this little pillar, well, you're limited by the size or angle of your tip. Okay, so if you've got a high aspect ratio tip with that very small angle down at the bottom of the tip, then you're going to be able to do a better job of figuring out what the width of that pillar truly is and what the angle of the pillar truly is. However, if you have a really broad, wide, fat tip, it's going to sort of convolve the tip with the sample, and so you're going to get sort of a convolution of your tip geometry with your sample geometry, which can be a limitation. Also, limitations are, for example, if your sample is too rough, then your piezo, it might exceed the limits that your piezo can move. So for example, for the AFM that we have here in Garwood Hall, the maximum peak-to-peak Z motion that can be done is about 10 micrometers, which isn't very much. And so if your surface is a rough surface with a large Z differences over a very short region, then you're just not going to be able to see it in an AFM. Now, that's not necessarily all AFMs have the same limits, but it does kind of give you a feeling for what the limitations of AFM might be. Also, it can't go to low magnification. So for example, for the AFM that we have here in Garwood Hall, the maximum lateral motion that can be done is about 100 micrometers or 0.1 millimeters. And so if you want a larger image than that, an image of a larger area than that, it's tough to get. Now, like I said, different AFMs have different limitations and can move different amounts. So if that's what you're interested in, you could go to another mode or go to another company and check on what they have available. But there are going to be limitations in that respect. Okay, that's pretty much summing up what I want to say, but I would like to give credit where credit is due here. A lot of the information that I presented in this talk came from a presentation by Wilson and Bullen of Northern Kentucky University, and it's a really nice brief PDF file that I'm going to put on our course website for you to read and access. It might contain a little bit more information that I didn't have time to go over in the talk. So credit where credit was due. That was a really nice publication. And as always, please do read your textbook. This is just AFM Basics. And I do want to emphasize that we offer a course here in advanced microscopy. So if you're interested in that kind of thing and you'd like to learn more about AFM or SEM or microscopy, advanced microscopies for nanoscience in general, please do sign up for that course in the fall. So thanks, and I'll see you in the next lecture.